Hi, this is Nimla Rednam. In this video, we are going to continue the topic squares and square roots, which is the fifth chapter in NCERT textbook class 8. Now here, this exercise of observing patterns, it's not only interesting, it is actually very useful in the sense, first you look at certain patterns in numbers and then you try to figure out is there any rule or a formula that fits and is it true for any given set of numbers, or is it true only for special cases, so on and so forth. This is one way of discovering mathematics. What are the rules that the numbers follow in mathematics? It's interesting as well as very significant method. Now here in square numbers, they have given a few patterns that they have observed, okay, that we can observe in square numbers, and we are going to look at the proofs of a few of them, okay, and then which is within the scope of our class 8, and then leave the rest for further analysis later on. So let's look at the first observation that they have made. Now you're already familiar with triangular numbers. That is, if you can see here these numbers 1, 3, 6, 10, 15, so on are called triangular numbers because if you look at the dot pattern, you can finish a triangle. Okay. Now using 3, this is the triangle. Okay. The next triangle is using 6. Now for example, if I take 4 dots, there is no way that I can complete a triangle with 4 dots, right? So that is to say that these numbers 1, 3, 6, 10, 15, so on are triangular numbers. Okay. Now that is a definition of triangular numbers. I need to be able to complete a right angled isosceles triangle with these numbers. Then you call it a triangular number. Now the pattern that we can see here is that if you combine any two consecutive triangular numbers, you will see that you can complete the square. Okay. If you were to actually physically make these triangles, you will see that if I fit this here, it becomes a square. Now, if I fit these 3 triangle over here, it becomes a square, right? So that is the first observation. Now they're saying that if we combine any two triangular numbers that are consecutive, okay, combine two consecutive triangular numbers and then we get a square number. That is the observation made. Okay. Now that is about triangular numbers. The second observation he is making is how many numbers lie between any two consecutive square numbers. Okay. Now here they have observed that, for example, they've listed down 1 square, 2 square, 3 square, 4 square, 5 square, and they're saying that between 1 square and 2 square, I have 2 non-square numbers. Between 2 square and 3 square, I have 4 non-square numbers. Between 3 square and 4 square, you can list down and see you have 6 non-square numbers, and between 4 square and 5 square you have 8 non-square numbers. Now here if you look at these numbers 2, 4, 6, 8, clearly you can see that these are twice of the first number. 2 times of 1 is 2, 2 times of 2 is 4, right? And 2 times of 3 is 6, 2 times of 4 is 2 times of 4 is 8, right? That means that between any two consecutive square numbers, you had twice the number in the first base, like 4 into 2, 8. Number of non-square numbers lie between 4 square and 5 square. Now, this is an interesting observation, and actually you can prove this using algebra. Now, you know that we already know that a plus b whole square expansion gives you a square plus 2ab plus b square, right? So, what he has done here is he has used that to find the difference n plus 1 whole square minus n square, and then if you look at this, let's solve this once and check it out. So here I have n plus 1 whole square, okay, minus n square. That is the difference between two consecutive square numbers, right? If I expand the first one, I have n square plus 2n plus 1 minus n square. So n square gets cancelled. I have 2n plus 1. This is the difference, right? Now the numbers that lie exactly in between, if you want that number, you need to subtract this 1, right? So you have 2n numbers. Now this is the algebraic proof for this observation that we have made. So if you look at the number line, okay, if I have the numbers 1, 2, 3, 4, 5, 6, so on. If I look at the comparison of that on the number line with the squares, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on. Now 1 square is 1, right? 2 square is 4, right? And 3 square is 9, right? So you can see that the gap here is progressively increasing. We are trying to understand this gap. Okay, let's look at 4 square as well. 12, 13, 14, 15, 16. Okay, so number of non-square numbers. So 4 square is 16. So between these two consecutive square numbers 9 and 16, you have the gap is increasing progressively with each pair, right? So if the question is asked how many non-square numbers exist between given two consecutive square numbers, simply you can use this formula that you can get from algebra and also from observation. Okay, so that is about the third observation that they made. Okay, right. So next, let's look at the next observation. So here, as we have discussed, they're saying there are 2n non-perfect square numbers between the squares of the numbers n and n plus 1. In specifically is calling those two consecutive numbers as n plus 1 because you're using the n in your formula over there. Now let's look at these, try these questions. How many natural numbers lie between 9 square and 10 square? Quickly you can tell, just now we have seen 9n and n plus 1. So 2n is nothing but 2 into 9, which is 18. So I have 18 non-square natural numbers that lie between are the same as the non-square numbers that lie between them. So without any calculation, you can say 18 numbers. You can check 81 and this is 100 and you can immediately see that the answer you have got is right. Between 11 square and 12 square, again without knowing the values of 11 square and 12 square, I can quickly say the number of natural numbers or non-square numbers that lie between these two are 2n, which is 22. Now, next question, how many non-square numbers lie between the following pairs? Again, 100 square and 101 square. I need not calculate these squares. I can quickly say that the number of non-square numbers between these two are 200 and between these two are 180 and over here it is 2000, right? Simply twice of the first number. Now here this holds true whenever you have two consecutive perfect squares, that 100 square and 101 square. 90, the next to 90 square, we know that 91 square is the next perfect square, so forth, right? So that is how you solve this question. Now the next interesting pattern that they are talking about is about sum of the first n odd numbers. You will see that in fact in higher classes, you will have it in arithmetic progression. Sum of first and odd natural numbers is n square because you will see that the first term is 1 and the common difference is 2, and when you add them using the formula, you will get n square. Now this as an observation, what they are doing is, okay, if you look at 1, you have 1 square, 1 plus 3 is 4, which is 2 square, 1 plus 3 plus 5 is 9, which is 3 square, so on. You can quickly check that it holds true, okay? And now what is the proof for this? Like I said, you will have it in arithmetic progressions. Now looking at it in a different way, what is saying is if the number is a square number, because it is a formula, the converse is also true. That is, if you have a square number, then you can write it as a sum of successive odd numbers starting from 1. Okay, so that also can be done. Okay, so now you have something called successive subtraction. That is, what they will do is, If you remember in the last video, we looked at the ones digit or the units place and we decided whether a number is conclusively not a perfect square, and there might be a possibility that it is a perfect square depending on the ones digit, right? Now here, if a random number is given to you and the ones digit happens to be one of the numbers where there is a possibility of it being a perfect square, then how are we going to decide if it is a perfect square? Now here he is suggesting you successively subtract the odd numbers, that is 1, 3, 5. Okay, successively subtract the odd numbers. If you end up in 0, then clearly it is a perfect square. That means it can be written as a sum of successive odd numbers. If you don't end up in a 0, that means it is not a perfect square. Okay, the logic here is that every perfect square can be written, as sum of consecutive odd numbers, right? Now, if the given number has to be a perfect square, if I'm successively subtracting all the odd numbers, I should end up in 0. If I don't get a 0, it's not a perfect square. Now, that is one way of checking, right? So, here they're saying that if a number cannot be expressed as sum of successive odd natural numbers starting from 1, then it is not a perfect square. Now, using this logic, let us check whether these numbers are perfect squares or not. Now, clearly here they have deliberately given all the ones digits as the ones where our first observation that we made in the last video fails. That is, if a number ends with 1, and we've checked 4, 5, 6, so on, then we saw that there is a possibility that it is a perfect square, but we cannot conclude for sure, right? In such cases, we can use this successive subtraction method. How do we use it? Let's take 121 for example. What we are going to do is, if I take 121, first let me write down the odd numbers, right? I'll start with a few odd numbers. Now from the given number, I have to subtract. I'm going to get 120, right? Now from 120, let me subtract the next odd number. I'm going to get 117. And from this, I'm going to subtract the next odd number. I'm going to get 112. And from that, I will subtract the next odd number. I'm going to get 105. From that, I'm going to subtract the next odd number. I'm going to get 96, right? And then from 96, I'm subtracting the next odd number. I'm going to get 85. Okay. From 85, I'm going to subtract the next odd number. I'm going to get 72. From 72, I'm going to subtract the next odd number, 15. I will be getting 57, right? From 57, I'm going to subtract the next odd number. Okay. I'm going to get 40. From 40, I'm going to subtract the next odd number. I'm going to get, this is 21, right? And from 21, can you see? Yes. From 21, I'm going to subtract the next odd number. I'm going to get 0. Now here you can see that I have got, in the end, I got a 0. That means that this number 121 is a perfect square. Now that is one way of doing it. It is elaborate, it is very lengthy, but in the exam, if they ask check using successive subtraction whether the given number is a perfect square, you have to do this. Now you can see that you can check that I have 11 odd numbers here. That means 11 square is 121. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 steps. That means 11 odd numbers have been added to get 121. That means that 121 is nothing but 11 square. In fact, if they ask you if it happens to be a perfect square, what is that number? Then you can quickly say it is 11 square. Okay. So that's about successive subtraction, right? And similarly, you can check that. So I'm going to quickly write the answer. This is a perfect square. You can check this is not a perfect square, 81 is a perfect square, 49 is a perfect square, 69 is not a perfect square. This is one way of checking whether the given number is a perfect square. Okay. Next observation that they have made, um, this is regarding odd perfect squares. Okay. Now for any given odd perfect square, I can write it as a sum of two consecutive numbers. Okay. So that is what they're saying. Let me highlight that first. We can express the square of any odd number, that is all the odd perfect squares, as sum of two consecutive positive integers. Okay, sum of consecutive two positive integers. Now here, how do you get that? You're simply, how you're going to start is, you have the perfect square, right? Now, if this is odd, if I add or subtract 1, okay, it is going to be divisible by 2 definitely, right? And you can also see that when I add these two, this plus half, this minus half will get cancelled. N square by 2 plus n square by 2 is going to give me n square, right? That means that I can write any odd. This is true only for odd. The reason, can you think of the reason? The reason is that when I add 1 or subtract 1 for an odd number, it will be divisible by 2. But if I do that for an even number, it won't be divisible by 2. So these two fractions that I have won't be natural numbers or positive integers anymore. And so this observation won't hold true for even. As long as it is odd, I can write it as sum of two consecutive natural numbers, right? Now here, how do you know these are two consecutive? You can clearly see that if I add 1 to this, I'm going to get the other one. Therefore, they are consecutive. Okay. Now, how do you find out these two consecutive? For example, in the exam, they ask you write 121 as sum of two consecutive natural numbers. How do you find it? I know this formula. So, I know that if I have the number is 121, then it is 11 square. That means that I have 11, my n is 11. Therefore, 11 plus 1 is n square is the 121 plus 1 by 2. So, whatever is given to me, I will add 1 to it. I'll get 122 by 2 is going to give me 61. Okay, plus the previous number minus 1. So, 60. Clearly, you can see that these are two consecutive natural numbers and the sum is 121. Okay. So, in the question, if they ask you to write a perfect odd perfect square as sum of two consecutive natural numbers, you have to remember this. You simply add 1 to the given perfect square and divide it by 2 and then the previous number. The sum, you can immediately check that it happens to be the same number, right? So, these questions are based on this. Express the following as sum of two consecutive integers. Whenever they ask you to express a sum of two consecutive integers, obviously they will be giving odd perfect squares. Okay, so here you can see that 21 square is given to us. And how will you do that? First, I'm going to find out 21 square and then I have to add 1 to it and divide it by 2, right? Let's do it. First question is 21 square, right? So, what is n square? 21 square is 441 plus 1 by 2, okay, is 442 by 2, which is nothing but 221. And the number before this is 220. Now, clearly you can see that sum of these two is nothing but 441. So, the two consecutive numbers they are talking about are 220 and 221, right? So, here that is the first question. Next, 13 square. So, 13 square is 169 plus 1 is 170 by 2 is 85, right? So, 85 plus the previous number 84, you can quickly check that it is nothing but 13 square, okay? Next, I have 11 square. 11 square we have just done. You have 11 square, we already have the answer. We just did it as an example. It is 60 plus 61 square, right? And then 19 square. Okay, 19 square is 361 plus 1 by 2 is 362 by 2. which is nothing but 181. 181 plus 180 is clearly 361. So this is about the first try these question. Now here, once you start this topic squares and square roots, it's advisable and it's going to be very useful even in all other topics for you to remember and be very thorough with at least the first 20 square roots, first 20 to 25 squares, perfect squares. Okay, you have to be very thorough with in the sense, if you look at the number immediately, you should be able to tell what is the square root of that, at least up to 25 squares, right? Perfect squares. So that is advisable. I would definitely suggest you to do that. If you kind of look at those perfect squares every day for a few minutes and try to recite them, you will be thorough with it within a matter of few days. Okay, so that is the first try these question. Next, they have asked, do you think the reverse is also true? That is, sum of any two consecutive positive integers is a perfect square of a number. Do you think that is possible? Let us check randomly. 5 plus 6, it is 11. Clearly you will see that that's not true. No, it's not true, right? That any two consecutive numbers don't add up to a perfect square, right? I've shown you just now in the number line. There are far and few in between in the number line, right? The perfect squares. It's not very common. And as the number increases, the distance between two perfect squares is going to become larger and larger. So adding any two consecutive positive integers won't give us a perfect square all the time. Okay, so that is about the fourth observation, fourth interesting pattern. Next we have product of two consecutive even or odd natural numbers. Now this is true for any product. It is not a perfect square, but it is one less than a perfect square. In fact, it is an identity in algebra. Okay, if you add any two consecutive even numbers or odd numbers, you get a square minus 1, which is one less than a perfect square. One less than a perfect. That means if you take in other words, you can say that if you take any perfect square, if you subtract 1 from it, then that number can be written as product of two consecutive even numbers or odd numbers. In fact, you can find it immediately. A square minus 1 is nothing but a plus 1 into a minus 1. That is to say, for example, I have 11 square. Take 121, right? 11 square is 121, right? Now, what is 121 minus 1? It is 120. Now, this can be written as product of two consecutive even or odd. Clearly, they're talking about even. In fact, you also know what those are. Now, here a is 11, right? So, what is a plus 1? A plus 1 is 12 and a minus 1 is 10. So, these are the two consecutive even numbers whose product is going to give me 120, which is one less than a perfect square, which is 11 square, right? So from this, you can make an interesting observation that whatever perfect square is given to you, the number to the left of it on the number line, when you subtract 1, it is always a composite number. Okay, it is not a prime number, because I can write it as a product of two consecutive even or odd numbers, right? So that is one observation you can make out of this. So this is about the product of two consecutive even or odd numbers, right? Now moving on to the next one. Of course, here when I'm talking about the number left to it being a composite number, it won't hold true when a is equal to 2. For example, let me quickly. So the first perfect square is 1 square and the next one is 2 square, right? And then we have 3 square and so on. So I'm saying that anything to the left of a perfect square is always a composite number. That won't hold true for 1 square, and because 1 square, there's no natural number to the left of 1 square, and for 4 also it won't hold true. But other than that, for all the higher perfect squares, it's going to hold true, right? So that is about fifth interesting pattern. In the sixth one, what they have done is they are looking at the perfect squares made out of ones. That is 1 square, 11 square, 111, 1111 and so on. Okay, and they're looking at the pattern. Okay, you can see that you can clearly see that there is a pattern. Now, in order to prove this pattern or see how you've got it, you can go into, algebraic expressions, expansion of, binomial expansion and everything. But as of now, for now, let us simply look at this pattern and answer the questions. Now, here you can see that as many ones as there are in this base, okay, that will be the center number. And from there, you're going to go in the descending order in both ways up to 1. That is the square of that particular number, right? So here if you see, write the square making use of the above pattern. Here how many ones do we have? 1, 2, 3, 4, 5, 6. So for this what I'm going to do is, let me write it here. 1, 2, 3, 4, 5, 6 square is equal to, first you write 6, okay, because these are the number of ones I have in the base. And then you write in the descending order 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. That's your answer. Okay, you can check in the calculator. Next, I have 1, 2, 3, 4, 5, 6, 7. Okay, so 1, 2, 3, 4, 5, 6, 7 ones square is equal to, because I have 7 ones, let me write down 7 first. Okay, and then 6, 5, 4, 3, 2, 1, 6, 5, 4, 3, 2, 1. That's it. That's my answer for this question. So looking at this pattern, you can see that this is the answer. Now the another pattern that they have given is, you have 7 square is 49, 67 square is 4489, 667 square is 444,889. Okay. So now you can see what is the pattern here. When I have 1 6, I will have 2 4s and 1 8. When I have 2 6, I will have 3 4s and 2 8s. When I have 3 6, I will have 4 4s and 3 8s. Okay, when I have 4, I will have 5. So here, this one corresponds to 2 here. 2 6s corresponds to 3 4s here. 3 6s correspond to 4 here. Okay, and 4 6s corresponds to 5 here, and so on. So you can see that it's strictly following this pattern, right? Okay, so now from this, can you tell what is the square of this number? Now, how many 6 do you have here? 1, 2, 3, 4, 5, 6. Now, because I have 6 sixes, okay, I'm going to write 7 fours. Okay, I have 6 sixes, so I'm going to write 7 fours. 1, 2, 3, 4, 5, 6, 7. Right? And after writing 7 fours, how many 8s will you have? One less than this. Like you can see here it's 1 8, here it is 2 8, here it is 3 8, here it is 4 8, here it is 5 8. So how many 8s I'm going to have? I will have 6 8s. 1, 2, 3, 4, 5, 6 8s. And then finally I will have a 9. So that is the answer here. Now here how many 6s do we have? 1, 2, 3, 4, 5, 6, 7. Right? So I'm going to have 8 4s. Okay. 1, 2, 3, 4, 5, 6, 7, 8. And then 7 8s. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to have a 9 in the end. So this is going to be my answer, right? So this way, even in the textbook they have, even in the exercise they have given a few patterns and asked us to fill out the remaining blanks that they have given. Okay, so let's just quickly start the exercise, right? So here I have, it's a, we can quickly finish it off. It's a very small exercise. What will be the unit digit of the squares of the following numbers? Okay, so this we have done already. Here the units digit is going to be 1. Here the units digit is going to be 4. Here the units digit is going to be 1. Here the units digit is going to be 9. Here it is 4 square is 16, so 6. 7 square is 49, so 9. 8 square is 64, so 4. And here I'm going to have 0. In fact, I'm going to have 2 zeros. Here 6 square is 36, so 6. 5 square is 25, so 5. This is the units digit of the square. Now next question. The following numbers are obviously not perfect squares. Okay, because they end with 2, 3, 8, 7 and odd number of zeros. Okay, what is the reason? That is the reason. We've already seen the numbers that end with 2, 3, 7, right? And 8, and also odd number of zeros are not perfect squares. So that is the reason that these numbers are not perfect square. So our reasoning is purely based on the units digit, and if it happens to be a 0, how many number of zeros it has, right? That is the reason. Next, third question, the squares of which of the following would be odd numbers? Okay, now you know that if an odd number is squared, you get an odd perfect square, right? If an even number is squared, you get an even perfect square. So here, if this number is odd, clearly the square is also going to be odd. This is even, so the square can't be odd. This is odd, so the square is going to be odd. This is even, so the square is not going to be even. Even if you look at the last digit, since you already know what the last digit is, you can quickly check, right? Here it is 1, here it is 6 for the square, right? So that is the third question. Next, observe the pattern and fill in the blanks. Now here, what is the pattern? When I have 1 0, I have 0 2 0. When I have two zeros, I have 0 0 2 0 0 in between, wedged between the two ones, right? So here I have 1 2 3 4 zeros. That means here I'm going to have 4 zeros, and here also I'm going to have 4 zeros, right? And here how many zeros do we have? 1 2 3 4 5 6. When I have 6 zeros, I will be having 1 2 3 4 5 6 zeros followed by a 2, and again 1 2 3 4 5 6 zeros followed by a 1. So this is your answer, right? Next pattern that they have given is, you will have numbers like this. Okay, when you have 1 0 1, it is 1 0 2 0 1. Okay, so if I have 0 1 0, I will have 0 2 0 3 0 2 0. Okay, so basically how many zeros I have here? For example, here I have 1 0, so the middle digit is going to be 1 plus 1 2. Here I have two zeros, so the middle digit is going to be 2 plus 1 3. Here I have three zeros, so the middle digit is going to be 3 plus 1 4. Okay, and then the pattern should be followed. That is, after 4 here I have to write 0 3 0 2 0 1. Similarly here 0 3 0 2 0 1. You can check if this is correct or not in a calculator, right? So that is the pattern. Now here, what is the middle digit I have? I have a 5 here, right? That means that I'm going to have 5. I have a 5, that means I'm going to have 4 zeros in your base on the LHS, right? So I have 1 0 1 0 1 0 1 0 1. This is 4 zeros, right? Right. So this is the base on the LHS square. Okay, that is the square, right? Next question. Now they have given another pattern. Now here, what is the pattern? You see that 1 square plus 2 square plus 2 square is 3 square. 2 square plus 3 square plus 6 square is 7 square. 3 square plus 4 square plus 12 square is 13 square, so on. Now you can see that the first two terms here are, the bases are consecutive numbers, 1 2 2 3 3 4 4 5, so on. So clearly this is going to be 6. Okay, so that is the first observation. Next, can you say anything about the third term on the LHS? Now here the third term is 2, right? Here the third term is 6, right? Now is it related to 2 and 3? You have to think about it. Here it is 12. Is it related to 3 and 4? And this 2, is it related to 1 and 2? In what terms? Is the addition going to give you 2? Clearly no. Is the subtraction? No. Look at the product. If you look at 1 into 2, it is nothing but 2. 2 into 2 is nothing but, let me write it here, 2 into 3 is nothing but 6. 3 into 4 is nothing but 12. That means here I am going to have 4 into 5, 20 as my base, right? So that is my second observation, that the third term is a product of the bases of the first two terms. Now the next here, in that sense, in this I'm going to get 6 into 7 is 42, right? Now what about the RHS? Is that also related? Is there a pattern there as well? Let us check. Now when I have a 2 here in the base, I have a 3 here. 6, 7, 12, 13, 20, 21, 30, 31. That means here it is going to be 42, 43. That is, this term, the base on the RHS is nothing but the next natural number to the third term base, right? So that is the pattern you can see here. It's very interesting because you have a relation between perfect squares here, okay? So like something like the Pythagoras theorem, where you have relation between perfect squares, you have Pythagorean triplets. This, in this case, you have 4 terms and you see a relation between them. Next, without adding, find the sum. We have already seen sum of n consecutive odd numbers is n square. Sum of n consecutive odd numbers is n square. So here I have 1, 2, 3, 4, 5 consecutive odd numbers. So the answer is 5 square, which is 25. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the answer is 10 square, which is 100. Okay, here I have, up to here it is 10, 11, 12. So it is 12 square, which is nothing but 144. So that is how you find the squares without actually adding the sum. Okay, next, in the 8th question, they're saying express 49 as a sum of 7 odd numbers. Clearly, you will be able to express it because 49 is 7 square. So the answer is 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. You can quickly check if it is 49 or not. Okay, so this is about the 49. Next, 121 as sum of 11 odd numbers. Again, it is the same thing. Let me write the 11, 7 first, and then after that, this is the 7th odd number, this is the 8th odd number, this is the 9th odd number, this is the 10th odd number, and this is the 11th odd number. So you get up to 21, odd numbers up to 21. You add them, you will get 121. Now, how many numbers lie between squares of the following numbers? This also we have in one of the observations, that when you have 12 square and 13 square, how many non-perfect square numbers, or in any natural numbers, how many natural numbers lie? The answer is 2n, right? So 2 into 12, here the answer is 24. Here it is 2 into 25, the answer is 50. You can quickly check actually whether it is correct or not. For example, 144 and 169 are the perfect squares here, right? So 144 plus 24 is going to give you 168, plus 1 is going to give you 169. So you can do that quick check. 2 into 99 is the answer here, which is nothing but 198. So that is about exercise 5.1. So in the next video, we will look at how to find square of a number using algebra, that is using, algebraic expression, expansion, using the identities a plus b whole square and so on. I will also look at few other interesting patterns, most importantly Pythagorean triplet, and we'll try to finish 5.2, right?